This is intended as a slide to reference while you read the article. You may even want to come back to this video to reference what I'm talking about for this article. Maybe check the note sheet on the PowerPoint. I've put in some additional information there. Reading research can be really hard and really frustrating, and you come across a lot of terms that you're like, don't know what that means. I still come across terms that I don't know what they mean all the time. So even some of the terms that I've put in here, right, I had to refresh my memory on, wait, what does that mean? So that's all this is it's some terms to help you understand the article better. So first is, what is a random effects model and why use it? So that's the model that is used in this meta-analysis. So first, a couple of reasons you would use it. So a meta-analysis has lots of different studies that it's sort of trying to combine the results of, right? A random effects model helps to account for varying effect sizes, right? Each study has a different effect size. The relative risk in each study is going to be different, so it helps account for that. It also helps to account for within study variation and between study variation, right? So in each study, right, there's going to be a confidence interval, but also between studies, the confidence intervals are not going to be the same. It's similarly to the exercise or the effect sizes are not going to be the same. And so a random effect model helps to account for that variability. So the goal of using it is to estimate a mean effect size across the studies, right? So I kind of want an average relative risk across all of these studies. Um, uh, so an average relative risk for whatever my intervention is. So in this case, it's going to be physical activity. It also allows for the inclusion of fixed effects as well as random effects. So a fixed effect is an effect that you expect, right? I would expect physical activity to have an effect on insulin resistance and type 2 diabetes, right? I'm not maybe as confident that race is going to have an effect on that development, despite what we've looked at earlier and what we'll look at in the coming week, right? Theoretically, I would think human physiology is relatively consistent. So I might use a fixed effect for physical activity, but I might use a random effect for race because I'm not sure um, what error race might introduce into my analysis. And I want to isolate my analysis to um, my variables of interest. Okay. So what this does is when you use a fixed effects and random effects is it results in larger confidence intervals, which makes it less likely that you're going to find statistical significance, right? So we talked about how if a confidence interval contains one, right, then it's not statistically significant. So when you increase your confidence interval range by using a random effects model, you're actually making your results more robust. Because then if you find statistical significance, right, it means that, okay, there really must be something here because I've done everything I can to account for error. Okay, what is weighting is next. So weighting means that a single data point may impact my results more greatly than another data point. So, and you'll see them reference that in the article. So I just want you to understand that the weights are proportional to the amount of variance between the studies. And I don't even think it's super critical that you understand that. It's just critical that you understand that not every study influences the results in the same way. So we did talk about that in class for sure a week or two ago. And I showed you some of the squares on a meta-analysis are going to be bigger than others. A larger square would indicate that that is weighted more heavily. Okay. What is a relative risk? So relative risks, just as a reminder, are a ratio of incidence rates. Okay, so an incidence rate is the number of cases in that portion of the population. So I'm going to look at the incidence rate of the exposed people, for example. So they're exposed to high amounts of physical activity. So I would look at, in the case for the article this week, I would look at individuals who contracted type 2 diabetes. So that's my new cases over the people who were highly physically active. So that would be the incidence rate of my exposed group because they were exposed to high levels of physical activity. Then I want the incidence rate of my unexposed group. So they were not exposed to physical activity. So the number of cases of diabetes in the individuals who were not exposed to high levels of physical activity. And then when I compare those two ratios, so I would put the incidence rate of the highly physically active group above the incidence rate of the not physically active group, that will give me a relative risk. Okay, so make sure that when they're talking about relative risks, you understand what's the exposed group and what is the control or unexposed group. They also talk about using the natural log of a relative risk for a normal distribution. Don't get too hung up on that. All it means is that if I were to plot relative risks, I would never expect there to be a normal distribution. So instead, I convert the relative risk into a natural log to look at normal distributions across studies. Okay, an odds ratio we talked about earlier, right? So you're grouping individuals based on the presence or absence of disease or some health outcome, in this case, type 2 diabetes. And then you're going to look at the prevalence of possessing risk factors in those individuals. So it's like relative risk, but it's prevalence rather than incidence. Okay. I think that's the last big one. Okay, great. So moving on to diagnostic criteria for diabetes, it mentions that diagnostic criteria changed during the study period. So in 1997, fasting blood glucose was diagnostic criteria for diabetes, so 126 milligrams per deciliter on 2 separate tests. In 2011, that changed to glycated hemoglobin at a level of greater than or equal to 6.5%, and or an oral glucose tolerance test greater than or equal to 200 milligrams per deciliter. So you'll just see that they talk about the diagnostic criteria for diabetes. I wanted you to be familiar with what that is. Nonlinear dose response is examined using cubic splines. Okay, so again, really random. I had to look this one up. So, but because it comes up, I wanted to address it. It means that they suspected a non-linear association and tested if a polynomial would fit the data better. Now, if you don't know what that means, that's okay. A linear association would mean, right, I could draw a line straight across. Polynomial associations, I might have some type of a loop involved, okay? So it's just a different mathematical process to look at associations. And as a result, or in combination with the comment on cubic splines, they talk about a likelihood ratio test. All that does is it compares the linear model to the linear mixed effects model. So that's where we were talking about random versus fixed effects, right? And so if you're just looking purely linear, right, then we want to know if the linear model or the linear mixed effects model or the polynomial model is most accurate. Okay, so the likelihood ratio test is going to compare your models and see which one is the best. Heterogeneity comes up a lot in this. So that's denoted in the research by an I-squared statistic. And it's a ratio that tells you the proportion of the variance in the observed effect that is due to the true effect. Okay, so here's an operational definition down here. So if the I-squared is less than or equal to 50%, studies are considered homogeneous and a fixed effect model can be used. Okay, so if I have a homogeneous study, then I can use a fixed effect model. So I don't need that linear mixed model and I don't need that polynomial model, right? But if the I-squared is greater than or equal to 50%, and then the heterogeneity is high and a random effect model should be used. Okay, so you'll see that come up where they sometimes talk about, ooh, there was heterogeneity, but if we removed this one study, then there wasn't heterogeneity. Okay, and they'll talk about how the results shifted. if they were moved to study. And then lastly, oh, not lastly, second to last, the Eagers test. The really simple way to think about this is to see if the distribution of the study results is normal. So when I'm examining a large number of studies, if I plotted them, I would expect them to look like a pretty normal curve. The Eagers test actually uses a triangle. So again, I'm just going to read this for you, but it's used to assess the potential for publication bias. Publication bias is when the outcome of an experiment or research study biases the decision to publish. So publishing only results that show a significant finding disturbs the balance of findings in favor of a positive result. Okay, that's a lot of jargon. All it means is that, and this is a very real thing, oftentimes publishers and journals want articles that show positive findings and they show what the researchers expected, right? That is significant. However, it's really important that we report non-positive findings so that we see, okay, so that we can examine variables and have well done research. So an Eagers test is used to assess potential publication bias in a meta-analysis via funnel plot asymmetry, okay? So that's what I was talking about when I was talking about a triangle. So it's a scatter plot of the intervention effect estimates from the individual studies plotted on the horizontal axis against the standard error of the estimated effect on the vertical axis. So again, all it means is that we're essentially seeing a normal distribution. So I want to see that, okay, I didn't only publish positive findings, right? I found some non-responders. I found some negative findings. If I didn't, I should question, okay, maybe there is a lot of publication bias and I'm not actually looking at reality. I'm looking at what is publishable, okay? And then the last thing that you'll see in this article is a sensitivity analysis, which assesses how sensitive a model is to changes in its input and data. So is the model greatly affected by a single result? And this is a good analysis to do because if I have one outlying study that's really pushing the results in a positive direction, right? And I remove that and then I get no result, right? I need to know that. So what these researchers did is they created this model and then they took out one study at a time and said, okay, did that study significantly impact what model got produced? And I think in this meta-analysis, they found that there was no significant effect of any individual study. I think they maybe mentioned one Korean study, but in any case, if they took it out, it still didn't significantly change the results. And when you perform a sensitivity analysis, it just increases your confidence that the model that you got is correct. So all of this that I've just explained, the idea is to help sort of convince you as the reader of the research to believe in their study, to believe that they did correct analyses, that their sampling processes were correct. So I hope that this helps you understand. Like I said, you can take a look at the notes in the PowerPoint as well, and you might get some additional context there. So enjoy the reading and feel free to reach out if you have questions.